Hi, my name is Tatjana Ljucovic. I got my Master of Science in IT Security, and since 2019, I work as security engineer at the Cyber Security Incident Response Team at G-Data Cyber Defense. G-Data is an antivirus software company. And in my role, I focus on reverse engineering malware that affects our customers. I analyze how the malware works, and sometimes we monitor specific malware families. I also helped design and develop internal tools that help us evaluate incidents more quickly and accurately. And for this presentation, I split it in three parts. I will talk about, at first, much more basic stuff. I will talk about what is Viper, IoT malware, and about the incident where AcidRain appears. And after that, I will talk about a bit about reverse engineering and AcidRain itself. What are the characteristics of AcidRain and why is it worth to emulate it? After that, we will go deeper in more technical stuff. I will explain and show you how I emulate it and what is the result of it. The incident. Before I start to explain, to dive deeper in the incident where AcidRain occurs, I will explain what is Viper malware. And Mitre is a knowledge base of adversary tactics and tactics and techniques based on real world observations. And Mitre defines Viper malware in the category of data destruction. And data destruction means overwriting or deleting data from a device. And there's two ways to overwriting or delete data. First, the most common way is the logical way. This means when we drop a file into the trash bin. The the file still exists, but just the pointer to the file is deleted. So that's why we can't see the file on the desktop or somewhere else. And the physical aspect is when the operating system overrides a physical space with a new file. You still have the chance to recover the file, but just with special forensic tools. So it's not so easy and not always 100% clear that you can recover this file. And yeah, the overwriting or deleting files is really time consuming for Viper malware. Why? Because the Viper malware is scanning the whole dictionary, directory structures and skip first the critical system files. Because when the Viper malware would start with the critical system files and overwrite them, it is possible that the operating system freeze or shut itself down, but the data are still available, and you have a chance to recover it. Yeah, what happened? We all know that Russia initiated its military invasion in the early 2022, and one day before, on the February 23, um, a high number of destructive malware attacks the Ukraine network infrastructure. And within 48 hours, 4 new malware wiper were deployed. One of the four is AcidRain. They were followed by many more, but yeah, AcidRain was one of the first wiper malware against Ukraine. Fortinet shows with this picture, yeah, how the wiper malware occurs over the years. You can say maybe one wiper IoT wiper malware in each year, but 2022 a lot of wiper malware were deployed. They are not all targeting Ukraine, but the most of them. And yeah, what happened? The threat actors attack Viasat. Viasat is an American commercial satellite internet service provider, and they offers secure network for military and commercial. And the threat actors gained unauthorized access, and the over a misconfiguration in a VPN management server. To give a picture of the situation, we see here the VPN management server. They gained here the access, and over the VPN management server, they deployed AcidRain to the modems worldwide, Europe-wide, and it affects over 5,000 of wind turbines in Germany. They were completely destroyed. They just run in an autopilot. Right. The date of the incident was the 24 in the February, and it include first DDoS attack, and after that they are deployed the wiper malware AcidRain. And there was a big discussion that the military use the modems for the communication, this way for the communication, but someone correct the answer and say no, this was just a backup. So we have another way to communicate. It was just backup. AcidRain itself were detected in the middle of the March. There was a file uploaded to VirusTotal with the name UCROP, and researcher discuss it. That could be an acronym for Ukraine operation. And yeah, here we can see the modem. It was a SurfBeam 2, and I bought it in the internet from a German customer, and he explained me how he experienced the incident, and it was the same. First, he had not a stable internet connection, and after that, after maybe an hour, he already had nothing on internet connection, and the device was not responsible anymore. And in the SurfBeam, there's a flash memory. There's installed, and AcidRain overrides the flash memory. Okay, reverse engineering. I will explain what is reverse engineering. We all know the high-level language code. This means like Java or C, where the code is readable because of comments or function name or class names, and this helps us to understand to understand the functionality of the program. And to run the program, we need to compile it. And after the compiling, the program is in assembly code, and the assembly code needs to translate again in machine code. The machine code is the binary, the executable program. This is a way of a developer. For a reverse engineer, we go the way back. This means we have the sample, the binary, the malware, and we try to yeah refactor the code. This means we disassemble it in assembly, and from the disassembly we go to the decompilation. And the question here is, yeah, okay, the decompilation isn't it the same like the high-level language? It is not, because the threat actors, yeah, they don't want that we analyze their malware, so they try to delete all the when they compile their code, they delete all the function name, all the class name. They try to maybe to encrypt parts of the program, or they pack the malware. So it's not so easy for the reverse engineer to analyze the malware. And this is a way which goes reverse engineer from machine code to disassembly to the decompilation, and there the refactoring of the code begins. Yeah, why are we doing reverse engineering? We analyze the malware for our customers, for incidents, and for the law enforcement. And we are collecting the capabilities and the IOCs. This means where persist the malware itself, where the malware persists itself, and maybe the command and control server, where which IP is the malware communicating to. Yeah, this is what we are doing, and this information we give it to an antivirus software or to the red teaming. And we have two ways to analyze the malware. First, a static analysis. This means extracting many information without running the malware, like do I see strings to get a feeling about the functionality of the malware? Maybe we see an IP address, so we know the malware is communicating with a command and control server. And yeah, the other way, another way is reversing the code, like I explained before. And another technique is the dynamic analysis. This means with a debugger stepping through the execution path, or letting the malware running in a controlled environment, so we can see how the malware really acts. you always should do both, not only one. Yeah, okay, it's a dynamic analysis. Let the malware run and see how it acts, and you know everything. Um, this is not so easy because malware can check. Okay, I am in a virtual environment. So they can change their behavior and hide the malicious part of the malware. And this is always why you should both static analysis and dynamic analysis. The question here is, okay, Tatjana, why are you not doing this to the IoT malware? So it's not so easy because the dynamic part is not so easy because IoT malware runs on different CPUs. So yeah, we have on our computer an Intel CPU, and in the IoT world we have much more. As an example, we have the ARM CPU, and this is in smartphones, in IP cameras, in wearable devices, and so on. And we have another MIPS CPU, and this is yeah, in routers or in media player and gaming console, and we have much more like Power PC or Super H, and this is so you can't run the IoT malware on your Intel computer, on your computer where you have the Intel CPU. So this is why we need an emulation. Right. Before I start to explain what is AcidRain and how it acts, um, I will show you the firmware of the serve beam of the modem. I got the firmware from a researcher, and he extracts the firmware of the modem before AcidRain runs on it. We can see it on the left side, and on the right side we see after AcidRain runs on the modem. You can see the difference. Yeah, here on the right side, it's a little bit schematic of the repeatedness of the yeah of the hexa code, and we see it starts with FFFF 9D and FFFF 9C and FFF 9B. It counts yeah, down. Yeah, AcidRain is an alpha executable. This means it runs on Linux OS, and it's compiled on MIPS architecture. So we know it is compiled for maybe for a router or something else. AcidRain is statically linked. This means all library functionality included in AcidRain itself, and AcidRain is stripped. This means also that we don't have any information when we try to reverse AcidRain. Um, because this means there are no function name or variables name, and yeah, AcidRain shows similarities to VPN filter. This is of the stage 3 plugin. This is a destructive part of VPN filter, and VPN filter is combined with the threat actor group Fancy Bear, known as APT28, and this is why research yeah, say that acid rains probably are from the threat actor group APT28. How acid rain works. You can say AcidRain has four functionalities. This means AcidRain first it tries to hide it in a daemon process, so it's not visible. And if someone would see the process, it's not. Yeah, you could not terminate it over the terminal. And AcidRain starts to override storage devices. After that, it tries to override files, unlink them, and delete directories. And if AcidRain sees that it has root rights, it yeah, the functionality are switched. It start first with override the files, and after that it overrides the storage devices. After the override functionality, AcidRain starts yeah, a redundant reboot. This means AcidRain starts four processes and tries on four different ways to reboot the modem. This is a overview of how AcidRain works. To get a closer view of the daemon process, we see some logs about the emulated AcidRain, and we see a printout lookout of the beginning of the emulated AcidRain. And this lookout came from this system called write. And we see here, look, AcidRain wants to write lookout. This is the result here. After that, AcidRain use the Fox's call to create a new process. This means yeah, this means this child process. He creates a child process. Use the set SID to get new rights, and this is a part of the daemon process. And the exit syscall here in the end is for the parent process. So the child process is the daemon process, and the parent process is exit. This is the way how AcidRain starts the daemon process. After the daemon process, the child process, AcidRain starts to override storage devices. And for that, AcidRain generates storage devices names, a lot of storage devices names. And we see here in the beginning, it tries to yeah, it generates SD storage devices, MTD block devices from 0 to 99, then a block MTD block device, and so on, and loop devices. This is a Linux specific devices. And yeah, I will spoiler a little bit. With the dynamic analysis, I could see that they had a bug in their code, and every generated device name with 10, 20, 30 are not included because they had a bug in their generation, name generation. So here we can see an inside what I said before. On the right side, we see the firmware after AcidRain runs on it, and this is the reversed code on the top. we see the functionality how AcidRain generates the data to override. It starts at 0xFFFFFF and counted it -1 and goes yeah, and goes down and down. And this is exactly what we can see in the attacked firmware. In the middle, we see a bunch of syscall which is AcidRain, which AcidRain is used. We see here at the beginning it tries to open an storage device calls fstat to get information about the storage device and use the IOCTL system calls to get more information, to unlock the device, to erase this, and to override it, and so on. This is the process to override the flash memory. AcidRain overrides files, unlink files, and delete directories. And I will give you a closer look how a closer view how AcidRain tries to protect system relevant informations. He tries to skip these directories. These directories are system relevant for Linux OS. And after the skipping, it collects the information and overwrites the files and delete all the directories which are not, these are not included. And the next step of AcidRain is the redundant reboot, and how it looks I will show you. On the left side, we see just one reboot and one return. This is the view when I open AcidRain in Ghidra, just for reverse engineering. And Ghidra sees, oh, okay, we have one reboot here, and the system should be, shut down. So it ignores all the other code which could come after this first reboot. And first I didn't know that, I didn't see it. It was, I saw the redundant reboot just because of the dynamic analysis. I saw it and I said myself, okay, I didn't see it in the static analysis. Something is wrong here. After I knew the function of Ghidra, that it hides the code after the first reboot, you can config Ghidra that you can show everything. And here, this is after changing the config. We see for reboots, we see which reboot files should be executed. And I mean, this is a good example why both is really needed, the static analysis and dynamic analysis. And because of that, I had the firmware, I could see which commands were really executed or should be executed on the SurfB modem. It's just one reboot. So this means AcidRain, or this gives us the feeling that AcidRain does not know the system, the modem where it should be run. So it tries on a blind way, fire and forget. I just want to reboot. I don't know the system where I run. I just try my best. Okay, now the fun part of the presentation starts, and Yeah, maybe it can be really technical. Don't be afraid when you can't follow what I say. I try my best to yeah, to say it in easy words so everyone can follow me. Okay, like I said before, to emulate acid rain, we need an emulation where acid rain can run. And for this, I use Killing.io. Killing is based on Unicorn and or on Kemu. And Kemu is a widely recognized emulation tool. And Killing stands out as a significant cross-platform for emulator, and it ensures syscall emulation and effectively isolate the emulation from the host environment. So this means when acid rain runs in Killing, it cannot affect our host system. It cannot wipe our host system. And yeah, this is what we want. And I need to say, never run a malware in your host system. Never try to reverse it. Just use always use virtual environment. So you are really protect your host environment. So I use Killing and for the emulation, and I also use a Docker container. This is not a Docker container. It's not a virtual environment. Docker container runs on your host system and use the kernel and syscalls from your host system. So only the Docker container is not a protection. Definitely not. But in combination with Killing, we have the yeah, we have a good way to set up everything what we need to emulate acid rain, because acid rain we learned it, search for storage devices, and we can create with the Docker container, yeah, the some storage devices and map it in Killing. So this is the the overview of my project, and I use Python for yeah, for developing my script, and I called my project Killiat, and I love to give my project a logo, but I ran out of time to design it by myself, so I had a little bit help from ChatGPT. Now I will explain what you need to do to emulate acid rain with Killing. Um, in the bottom, you see that I call the class Killing, and Killing just need the path to your sample to acid rain, the path to the root file structure, file system, just a directory included with other directories. And if you don't know how to set up your rootfs, Killing has a lot of sample rootfs which you can download. And you also can say, okay, I want to log all this information in my log file. So the next is adding the files to the file system. you can from the static analysis I knew what acid rain need or work with. First is the null device, and two yeah two devices which I create. First, the SDA device. This is a block device. AcidRain, looks for two kinds of devices. First, the block device. SDA is a block device. This means the data is or written in block parts. And the other one is character-based device, like here the MTD device. It's typical for flash memory, like the SurfBeam does it have. And MTD files are memory technology devices, so they are character-based. And this is what I dynamically add to the system, and then I can run killing and start the emulation. And here we can see the beginning of the emulation, some logs. We see the write syscall with the lookout. We see the fork. I mean, this is a part of the daemon process. And here the child process starts. It uses the dev null file to map it to the three standard file descriptor. It is standard input and standard output, and the third one is a standard error. So AcidRain maps the dev null file. Everything what is read or what is written or works with the standard file descriptor, everything runs in a null. So you can't see something, you can't, there's no error output because of the dev null file. And after that, it starts to scanning the storage devices. Here, it's the first one is SDA, the block device, and it uses IOCTL, LC, and starts to write with, we saw it before, with FFFF, FFFE, and so on. So IOCTL is an IO control syscall which interacts directly with the storage devices, and the IO control use commands to work with. This is just an example here. And the next, what I wanted to say, the initial running or the emulation of AcidRain runs probably pretty good. Yeah, and there were no bugs or something, no issue, something like this. But this was a lie. One issue occurs, and this was an issue from killing itself. This means, AcidRain use the getDense syscall. The getDense syscall we can see here is a syscall which allows you to scan all directories in the system, the directory structure. So, and killing had a bug that because of improper memory alignment. So MIPS is a architecture which is a part of the RISC architecture family, and it is important that the data is correct aligned. And what does this mean? This means that the data access must be aligned according to the word of the architecture. This means the RISC architecture has a typical required alignment of 32 bits, or in other words, 4 bytes. And if the word is smaller than the length is smaller than the 32 bytes, it needs to be aligned. Yeah, a little bit complicated to explain, but it was just a small fix. I created a pull request in December. It's still open, so we had to put some patches here and to fix the code. But if we ignore this issue, AcidRain would emulate correctly from the beginning to the end. This means not that the malicious part is executed. For the malicious part, we need some hooks. And this was a little difficult part. You need to know what AcidRain is really doing to implement these hooks. And I had you need to implement the reboot and exec hook, and the most important is IOCTL hooks for block-based devices and for the character devices. And how it looks, this is here. First of all, because of AcidRain creates a new process, I need a hook for the fork. Just because in the fork syscall killing set this this variable of to true, and when the exec hook when the exec syscall is called, killing stops the whole emulation. You can see that killing runs still as a daemon process, but the emulation with killing stopped. So I don't had log information. I couldn't see anything. It looks like that AcidRain stops, but yeah. So we need a fix for the execute, and this was just the hook for the fork. We set I set this variable on false, so I prevent that killing exit simulation. And yeah, for the exec syscall was in killing not implemented. I just wrote a hook with here simulates the exec syscall and return it with null. So AcidRain thinks okay, the everything went well. The IOCTL hook looks a little bit more complicated. I told you that AcidRain uses the IOCTL hook to get information for the storage devices and overrides it. And these are the commands like block get size, mem get info, mem unlock, and so on. and I needed to implement the behavior because in killing it's not it's not implemented. So what did I need to do? Like in example, the memget info command. You need to read the documentation about the syscalls and the commands, and the memget info needs on the stack a structure, and it looks like this. In the memget info are information about the type, about the flags, about the size, erase size, write size, and so on. And I wrote, here's a type of an MTD device, can be something between 0 and I mean 7. You have 7 different types, and 4 is the flash device, the character-based, character-based device. I created it with hard-coded information and wrote it on my stack. So AcidRain had this information and thought when it called this syscall, oh, I have the information and now I will trigger my malicious part. Yeah, we know this graphic, this figure from before, the data override, which is generated here, and we see the MTD file. It yeah, gets some information with fstart, and then we see a bunch of IOCTL. We see memgetInfo in the emulation, we see memunlog, and I prevent everything on the I deliver everything in the stack, and AcidRain say, oh, okay, everything is fine. I can work here, and now I'm finished my erasing process and close the file. So this is a part to override the flash, and this is the firmware we can see again. So for the emulation, what I needed for it, I used tools like Killing, Docker, and Python as my programming language. We learned that the initial setup ran smoothly, but it triggered not the malicious functionality. We needed to implement hooks for it. Killing had a bug, so it's not so easy to emulate a malware, an IoT malware. You need to put a bit effort in it. But when you did it, because you wrote a script, so you can always run this emulation. With a dynamic analysis, we precise the the device names. We saw that we have a bug in the generation, the name generation, and that everything with the ID 10, 20, 30 were missing. We revealing the redundant reboot, and yeah, we can say we emulated AcidRain properly. So, but what mean emulated? You want maybe to see something. Now I will show you the evaluation part. It was if you want to see something in numbers to say, yeah, okay, I see AcidRain were emulated to this and this percent, and so for that, Killing provides a built-in feature to create a coverage file. The coverage file included a lot of information with how much function did I yeah, executed, and which execution path did I pass, and so you can everything with the coverage file you can visualize in IDA Pro with the Lighthouse plugin. Um, yeah, to see how good simulation works. So for me, it was important to run the AcidRain with different config, like I said before, with different storage devices types like character based, the flash device, or the block device the SD cards. So I this was important with 0 of, yeah, 4. It's just the type. 4 was the flash. And AcidRain was looking for root permissions. Does AcidRain have root or not? And this yeah, affect the behavior. Yeah, and the result? Ah, the coverage feature was just for one process. So this means the implementation of the emulation, yeah, the emulation was complete, but there was still a little bit work to do, because for the different processes, and yeah, we need to do something. So what was the problem? The coverage file for in killing were generated, but only the information from the first process were included. This means when the child process came and had more information, the write blocks, one table in the coverage file, were not updated anymore, because the one process was exited, and that's it. So I need a little hook or a function which creates a coverage file. This means a little technique to update the coverage file. And the important things was that the basic block table was not updated. Basic blocks are a bunch of instructions, and yeah, I needed to implement that. And then I saw, okay, I see how many instruction has AcidRain, how many basic blocks, and how many function. AcidRain has 86 function, and executed were 67. This is an emulation success of 73. And on the left side, on the right side, we see the different results with different configuration, if it's root or not, and which storage device type the storage device type AcidRain found. So in a total number, it was 73. Yeah, 73%. Okay, the question now is, yeah, it sounds pretty good, but why not more? This is because of the library function which were included of AcidRain, and there are some library function which AcidRain never needed. So yeah, this is why it's just 73%. But if we are looking AcidRain, just the core of AcidRain without the library function, we see that AcidRain is a really small IoT malware. It has 12 functions, and 96.60 person were emulated. And this is really pretty good. And just few instructions were not emulated, and these are just error exception pass. So because it runs probably some instruction for the error handling were not executed, and this is why here's a little gap. So in AcidRain, we see a view of, in IDA Pro, we see a view of the coverage file, and here we can see the result. The function name in the bright area are the AcidRain core function, and we see here the instruction how many were executed. So, and we see here 100%, 100%, 94%. I think it's a really pretty good result. And here is a small view about the process. We have the parent process, which is in total just 2% of AcidRain, and we see this child process with the overwriting functionality is 90% of AcidRain, and the reboot process, AcidRain creates always a child process for this, are 1.2% in total. So this was his emulation and the result. So we learned today what is a wiper IoT malware. We got a closer view on the incident with Viasat. We learned about the importance of static and dynamic analysis and why we should always do both. We got a pretty deep insight of AcidRain. We also saw that we had an emulation success of AcidRain with 73%, and the core was 96%. I thank you for your attention, and if you want to read about what I talked in our blog cyber.vtf, you can read it. I started to wrote it in a 3-part blog. The first part is already published, and the second part will come in the next week, so stay tuned. And if you want to see the code behind the code what I presented to you, you can visit our GitHub project. If you have question, feel free to write me or phone me, and I hope you liked the presentation. Have a nice evening.